Okay, so in terms of calculation with complex numbers, once you sort of get the hang of it, are not terribly difficult to incorporate into your intuition as far as arithmetic is concerned. But they can definitely be annoying sometimes. So it really does help to have some sort of calculator available if you're doing complex arithmetic. The syntax here is more or less what you would expect. So in Sage, the variables little I and capital I can be used interchangeably as the imaginary unit. So I just have little I squared here. So to square a number in Sage or Python generally, you can use this double star notation. And if we click evaluate here, we'll see that Sage already knows that little I refers to the imaginary unit. So little I squared equals -1. So we can now incorporate that into the definition of a complex number. And we can do a whole bunch of things with complex numbers. So here I'm defining the complex number 7 minus 15 times I. And we can do all sorts of things once we've defined a complex number z. For example, I can access the real part with the syntax z.real, open close parentheses. I can access the imaginary part with the syntax z.imag, open close parentheses. I can conjugate the complex number with the syntax z.conjugate, open close parentheses. I can calculate the absolute value with z.apps, open close parentheses. And I can calculate the reciprocal by just taking 1 divided by z. So I do all of that here. And so let's click evaluate and look at the result. So the complex number that I input by default here is 7 minus 15 times I. So that pops out here on the first line. The second line is telling me that the real part of this complex number, which again is given by the syntax z.real, open close parentheses, the real part is 7. And the imaginary part is -15. The conjugate, which I'm just printing out here as z to the bar, this is obtained by negating the imaginary part. So -15i plus 7 should get replaced with 15i plus 7. The absolute value here is the square root of 274. So remember, that should be 7 squared plus 15 squared under a radical here. And finally, the reciprocal of z turns out to be 15 over 274 times I plus 7 over 274. This makes sense because remember that the reciprocal has real part given by the original real part of the number divided by the square of the absolute value. So in this case, we should get 7 divided by 274, which we do. And then the imaginary part is the negation of the original imaginary part divided by the square of the absolute value. So here we should get 15 divided by 274, which is exactly what we do get. We can do arithmetic with two complex numbers. So we can add them together with the expected syntax, z1 plus z2. And we can multiply them together with the syntax z1 times c2. We see that here. So here I've defined z1 to be the complex number 7 minus 15i. And I've defined z2 to be another complex number, 13 minus 4i. If I click evaluate, this will print out the two complex numbers that I've defined and then give me their sum and their product. What else can we do? Well, we can study complex matrices and complex vectors. So there's nothing preventing us from filling up a matrix with complex numbers and filling up a vector with complex numbers. What might we want to do with all this? Well, we might want to take a linear combination of the columns of a matrix with matrix vector multiplication. The syntax there is just A star V, where A has columns that we want to take the linear combinations of, and the coefficients are stored inside the vector V. Another thing that we do super often is we take the conjugate transpose of a matrix. That's built into Sage with the syntax A dot capital H. So So remember, A raised to the H is a notation that some people use to refer to the conjugate transpose. So if I click evaluate here, we can see some data that I've predefined. So here I've predefined a 2x3 complex matrix called A. I've calculated A star by issuing the A.H syntax. So this is a 3x2 matrix obtained by not just transposing A, but transposing and then conjugating inside of A. I've also defined a complex vector here, the coordinates being negative I, 11 plus 2I, 19 minus I. So that's the complex vector that I've defined. And then the code will also tell me what A multiplied by that vector is. In this case, we get this new complex vector, which is in R2, because our original matrix was 2 by 3, and the vector we're using, it comes from C3. Finally, one thing we do a lot is we take the inner product of two vectors. To take the inner product of two complex vectors, we need to think a little more carefully than we did in the world of real numbers. We take the conjugate of the first vector, then we multiply all its coordinates by the corresponding coordinates in the second vector and add everything up. So here I've predefined two vectors, v1 and v2. These are complex vectors. And we can find their inner product with the syntax v1 dot inner underscore product v2. So if I click evaluate, I can see what the output is. So my first vector is the vector negative I, 11 plus 2I, 19 minus I. And the second vector is negative 9, 6 minus 4I, 5 times I. The inner product of these two vectors is apparently 72 times I plus 79. So again, it would probably be quite a pain to work that out carefully by hand. So it's nice to have a computer do some of that work for us. It's important for us to understand the definitions, and then it's good that we have computers to do the tedious calculations for us. So please use this as you're working on all the quizzes and homework and stuff.